I will, okay, I'm going to share my screen and hopefully I will get the right screen. I'll move this out of the way and let's see. Okay, can people see that? It says chapter 10, introduction to. Okay.
Yeah, we
It
can.
gave me the thumbs up, so we're good.
Works.
If I say something and you have a question, when I like to give presentations, I like to make them interactive. So please stop me, or I probably will. Let me drop the chat down, but I probably won't. And I'll move it over here. Now I've got so many windows on my screen. I don't know if I'll notice if you put something.
I can narrate if anyone has any questions.
Okay.
And you miss them.
Thank you, Ryan. Appreciate that. So anyway, we're going to start with chapter 10, and this is Introduction to Artificial Neural Networks with Keras. So let's go ahead and get started with that. Okay. As Ted kind of mentioned, we're transitioning, if you were with from chapters 1 through 9, to something a little different. We're going to focus on neural networks, which is, realistically these days, kind of where the sexiness, if we will, is in machine learning, for lack of a better term. But it's not all that different. It builds on the concepts in the first 9 chapters of the book. So, we'll just see how we go. Okay, so here's our agenda for today. And I modeled this on the way he did the book with great license from what Aurélien did. We'll first start with a quick introduction of biological neurons and neural networks, which is the incentive of why we have our artificial neural networks and neurons. And then we'll go into a demo on Keras and TensorFlow. And if you have any questions about it, feel free, like I said, just to stop me and ask as we go along. Any questions on that? Okay, good. Let's move on. So this is an animal neuron. If you're never, probably something you saw in high school biology, maybe it's been a while. For me, it's been a real long while. And what this is when you go out and you're working in your garage and you hit your thumb with the hammer, this is the thing that makes you go, ouch. This is how that signaling gets from your finger that you've now damaged up to your brain, and you go, ouch, and throw the hammer across the room or whatever you do and continue onward. You can see here on the ends, these dendrites are hooking to to your finger, various parts of your fingers, and the signal comes in. It goes through this the cell body here, the soma, and then if you watch here, this is a really cool illustration somebody had. It gets transmitted to an axon and then goes across what they call a synaptic gap. So that's great, but that's just one little cell. So what they do when they put them together in a neural network is they have a lot of these. So here you have one dendrite and maybe this other one, and then the signals are going down and getting amplified. And when they reach a threshold level, then you go, ouch. So there's kind of a gating mechanism going on, is all I'm trying to point out in this. And that gating mechanism in this structure is what was used to develop neural networks. So let's take a look at that and see how these compare. This is our artificial neural network. Like our little neuron, or the axon that I showed you, we have inputs coming in on one side. The magic happens here in the center. More about that for a second. And then an output that's conditioned on what's happening in here. So if you keep this picture in mind as to what it kind of looks like, then you can see it's kind of closely related, and you can see why they used starting from the human, they ended up with this structure. But that's great. But like I said, the magic happens here. So let's take a look at that. Now, if we look at this, we see we have a number of things. We have our inputs coming in, our input signals coming in. And for us, our input signals are going to be values. Let's say we have a data set. There are going to be numeric values coming in. We have some weights, And these are used to condition these signals. So, maybe if this is, we're classifying house prices or something, this is square footage coming in, and I2 is, I don't know, number of bedrooms, something or something, and we would condition these all together. We put them together, we have this bias term that we use, and then we have these weights, and these are something we will train with our neural network. So these have whatever they are, sort of random values initially, and we're going to adjust those. They get summed together, and they're kind of pushed through this equation. Now, this I here represents the vector that represents all of these values. In other words, it's, I1, I2, I3, dot, 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 IN. And these weights represent all these weight values here, W1, W2, W3, so on. Plus, we have this bias term. Go ahead.
Question about the weights. Those values were acquired from training. We're starting at the initial state, so they'll be in whatever initial state they're in. Okay.
Just consider them random for now, and we'll get to how we train them in just a moment.
Okay, got it.
Okay, cool. All right. And then eventually, we sum them all together. We multiply the inputs times the weights and add this bias term to it. Okay. And then finally, we have this activation function that we push them all through. So we have, here's our sum of our inputs and our weights, and we add the bias term, and then we have this activation. And then that gives us our output we put here. Any questions about that? Because it's kind of important we understand that. Go ahead.
Oh, go ahead.
No, go ahead, Vincent.
Okay. What does the activate actually do?
Okay, yeah.
Okay, go ahead. Fine.
No, go ahead.
So I see that you multiply the inputs and the weights, and then you sum them, and you add the bias, and then you do a final activate on it. Actually, it's kind of intuitive. Never mind. It's fine.
That's okay.
That's fine.
Yeah. Coming back to that biologic thing, this would be the thing. Remember I said, you have to kind of meet this threshold. This is where you'd either meet the threshold or you'd condition the output. Maybe you'd, divide it by something or whatever. But yeah, you're being a very good. Oh, go ahead.
It's deciding whether to it's deciding what to do, whether to give it a certain output or a different output, depending on whether it meets criteria.
Yeah, it conditions the output, maybe is a good way to phrase that or something like that.
That's probably better, yeah.
Okay. And go ahead,
if I could add, so we're not going to go through the history that was presented because it's too much material, but if it helps, the first idea people had was just, if it's over this, I'll put a 1. If it's less than that, I'll put a 0. Which is very simple.
Yeah, let's actually go to the next slide because I have that on the next.
Okay, perfect.
Okay, so back to the question on activation and activation functions. The original one, and the one he has in the book from the 1950s, is called the perceptron. And it's a step function. And as Ted was alluding to, it's kind of binary here. It says if X is greater than some threshold, then make the activation function just 1, right? So you just output the input. If it's greater than, or in particular, that's how they work. But in the perceptron, they went with greater than 0.5. So if you got like halfway there, then they put out 1. That 1. And if you remember, let's just go back here for a sec. Yeah. Oh, pretty. This is essentially acting as a, kind of a multiplier times that. So this would essentially, you want it at 1. You want the same signal to be output that the weights and everything added up to. I will point out that the use of perceptron and any sort of step function is fairly uncommon these days. You don't find them. Or what you find is the thing on the right side, and this is ReLU, called the rectified linear unit. There won't be a test on it. You don't have to memorize that, but you'll bump into it all the time. So I thought I'd put it in there. And essentially what you have is if X is less than 0, then it outputs 0. Otherwise, it outputs what's in X. Okay. And this is a parameter you set. There are dozens of activation functions. And this, as we'll see, this is like, there are so many knobs you can turn in a neural network. And this is one of the key ones. So let me move on and hopefully this will become more apparent. Okay, so back to our artificial neuron, as we talked about, here's our activation function. It's going to read what's in here and decide what we're going to output. Everybody cool with that? Good. Okay, now, but the power of that comes when we take all those neurons and we put them together into a neural network like this. So what we have here on the left, we have our inputs like we did before, but it's not just feeding like this neuron, we're feeding all these other neurons with its values. And the other thing is we're arranging our neurons into layers. Here's one layer over here, and in the center we have another layer. And on the final, we have another layer, which we term the output layer. So get used to using these terms, the input layer, which is not really a layer, it's just input data. The hidden layers, which are the ones that aren't input and output, I guess they ran out of good ways to make terminology, and then the output layer. And that depending upon what the output is, we may get multiple outputs, and these may go through other functions here that we work on. Let me go ahead.
The little orange circles. So is it safe to assume that's representing the whole I times weights, sum, bias, and then
yeah.
activation?
So,
okay.
Let me go back. I made my
Oh, okay, got it.
Got to get it here.
I just answered it. That just answered it. Yeah.
Okay. Thank you, PowerPoint. So yeah, you're absolutely correct. Each one of those orange things represents a neuron in this particular case. And as we'll see, we can have hundreds or thousands or millions, or I guess billions. I guess they're pushing close to a billion now in some of them. The interesting thing is, though, let's go back to that. Here, each one of those neurons has all these weights, right? That we will be training. So that's a lot of knobs and switches and dials and conditioning that we can do. So that's the big thing. Okay. So if we put that neural network over to the side, let's talk a little bit about how they work, how we train them. We train them with batches of input data. We might have like 60,000 rows of data. We want to push this through this, and we want to adjust those weights as we see different batches of data. How we determine how we adjust those weights is through the training is to minimize error. And we'll get to what error is in just a minute. Essentially, error is based on what you set to specify as error. So we go through all the data so many times, and we call those epochs in the data set. So if there's 60,000 rows in the data set, we're going to go through those 60,000 rows multiple times, each one being an epoch. So if you could just kind of keep that picture in your head. We will, however, go through them in clumps of batches. So we'll pick 60,000, maybe 100 in a batch or something like that. And we'll go through that first 100, and then we'll make some adjustments to all those weights and biases we talked about. How we make those weights and changes to everything is based on what we call a loss function. Excuse me, I have to take a drink of water. And that's how we measure our loss, which is a stand-in for error. Our goal here is to reduce our loss. And essentially what we're trying to do is tune those weights so that our model does better at predicting the output we would get given our inputs. How we do that is through something called an optimizer, which updates the weights to reduce that loss. And the most important thing to get out of this is the number of epochs, the batch size, the loss function, and the optimizer. They're settings we specify. These are tuning parameters that we make choices on. Okay? So keep that in your mind when we get to the examples, because we're going to see them. So how do we make, now that we have all this cool stuff, how do we do that? Well, we have a process we call backpropagation of error, or backprop. What we're trying to do is from the output, now starting on the right now and working back towards the left, we want to adjust the weights using the optimizer to reduce loss. So we want to work backwards, adjust this weight, adjust that weight, adjust the weights all the way through here to reduce this loss based on the loss function we specify. We'll see this in action, and it's much easier to probably understand. Okay, some notes on that. The order and contents of training batches change. Remember I said we had epochs and we had batches of the data, which were random samples out of the batch. When you run the next epoch through, maybe it picked the first 500 for one batch, for batch one last time. It may take, out of our 60,000, it may take the last 500 and make it the first batch, this next epoch. So that changes. So it gets exposed to all the data in our data set. Okay, and in terminology wise, when we have more than two of these hidden layers, we have what we call a deep neural network, just in case you were wondering what a deep neural network is. Questions, that's a lot. So if anybody has questions, please ask.
So one or less is not a deep neural network.
No, but it's still a neural network. Deep is just a naming convention, but I mean, people will, publish, whole things calling it, oh, it's not just regular neural networks, it's deep neural network, but it's just a naming convention, really,
Okay.
So, yeah, process is the same.
Okay. So say we have like a certain, so say we pass input through that neural network, it receives the output, and then from the output, it goes backwards and adjusts the weights for each layer, I guess, of the weights. And then that just repeats itself to like keep making it more accurate, I guess.
Yes, you're exactly, that's really insightful and correct. Yeah, we use that loss function, as I said, to measure our error / loss. And then using the optimizer we specify, we tell it the process it should go through to update the weights to reduce loss.
I see. Okay, cool.
Yeah. Cool.
Jerry, do you have another slide? Are you going to talk any more about backpropagation or?
A little bit, yeah. Let me. Okay. Actually,
I just thought.
I have some.
All the math, but I thought maybe just a little bit more.
Do you want to go into? I really don't have a lot of math yet. If you think we ought to go into it, other than to say that.
No, I'm not going to explain the math. What I'm just simply going to say is that for those of you who are familiar with calculus, we use what's called the chain rule. And basically there are partial derivatives. So the derivative of a function, if you just say like y equals x squared, the derivative for any value of x is the slope of that curve y equals x squared, which is a parabola. So it's the slope at any point x. Things get a little bit more complicated when you have multiple variables. So in this case, Jerry, right, has like n inputs and you've got a whole bunch of weights. But nevertheless, the same concept applies. You can say, what is the slope with respect to just one thing? And so that's called a partial derivative. And so in calculus, there is a principled way where you can say, for output number 1, what is the contribution of all of the different things to the left of output 1. And you can say, I'm going to say 10% goes to this weight, and 1% goes to that one, and 0.02% goes to this one, and 5% goes to that one, just by calculating these partial derivatives. And so then that tells you that, oh, well, if I was wrong and I want to, reduce the weights, the one that's 10% is going to get reduced a lot, and the one that's 0.02% is going to get reduced very little. So not all of the weight updates are going to be the same. And it's going to be done in a principled way because the calculus tells us how much each of those things contributed to our answer being either right or wrong. And so when we sum all of those up, that gives us the amount to tweak any individual weight up or down. And then in the first part, I don't remember when, but in the first part of the book, we did introduce this idea of gradient descent. And so then we take small steps in the right direction. We don't try to just in one jump perfectly get to the right answer, but we just take a small step in the direction that the gradients are telling us. Basically, for each weight, is it telling us to go up a little, up a lot, down a little, or down a lot?
Right. Yeah.
So how is the law of diminishing gradients applicable over here? Because at a certain point, right, as you keep on taking the derivatives, at a certain point that becomes 0, right? Is that the point when the neural network knows that it has learned enough?
No, you're referring to You remember the activation function we talked about at the beginning?
Right.
Yeah. So the purpose of the activation function is twofold. One of its purposes, though, or manyfold. One of its purposes is to avoid what you just described, which is called the vanishing gradient problem, if I understood what you said.
Right.
Which is, if you differentiate far enough backwards, you end up at 0, and you end up setting the weights to 0, and essentially you shut down the neuron. I believe that's what you were saying. Am I correctly assuming that? Or?
Yes. But
Yes.
the thing is, like, if you're running on a high number of epochs, right, eventually you'll run into that issue, right?
There are ways around that, and we'll get a little bit to that, but
Okay.
I really don't have anything specific to that. But yeah, there are methodologies for getting around that.
Got it.
And one is you see here with this random samples sort of thing. That's one of the ways, because if you keep passing different data to it, the numbers continue to change a bit. But,
Got it.
okay.
Thank you.
No problem.
I would like to mention, I would like to
No.
mention that knowledge of brain structure is not actually necessary to understand neural network. Also, historically, where it came from. You can use pretty much any hierarchical structure. And I would like to show what I once did. If I can I please share my screen?
So Maya, maybe towards the end, I'm a little worried about time and just getting through the material.
Oh, it will be very quick. It is very, very quick. I promise. So can I please share my screen? Jerry?
Do I have to do anything? Or?
Yes, you need to close your shared screen.
Oh, okay. Sorry about that. I was sitting there waiting for Ted to do something.
Okay. No, Ted cannot do this.
Okay. All right. Go ahead. I stopped sharing. So.
Okay. Thank you. Okay. Here it is. So, neural network could be very easily imitated by corporation chain of command. So you have people who gather different information about storage, about how many goods you have to sell in 1 week, about how much, about what budget you have, which you can spend on these things you buy, and then you should sell them. And you bring them to some manager, all this information you gather. And well, there could be several managers if your stuff with which you work is complicated enough. And they watch different indicators and they do different adjustment to the different conclusions from it. What is enough, what should be adjusted. And then it all comes to CEO, who finally compares all of these to what kind of is the key indicator. And then he needs to pass his conclusion to the managers, they pass them to other people. And so it is pretty much could be described in the same way as work neural network. So, and well, you see, you have hidden layers, and as in real life, hidden layers as middle managers do the bulk of the work and they're not known to anybody. That's it.
Okay, thank you very much. I love the oh, let's see here. So
You're
let me go
welcome.
back. I love the idea of saying the middle managers do the work, because we know that is. Okay.
I have a quick question. So there's basically like a column of quote unquote neurons, and that constitutes a single hidden layer. Are all the connections from one hidden layer to another hidden layer like the same, or are they more like random or scattered, or like can one just connect to the other connect to two, the other connect to three, or do they all have to be?
At this basic level, let's just assume they're the same, if that's okay.
Okay.
Yeah,
Okay.
obviously other architectures have various conditionings and you know, skipping of layers and things like that they will do. But I think that's a little far advanced for where we're at right now.
I see.
In this general simple architecture, all the connections are between layers, and they're consecutive layers, and every neuron is connected to every other one in the next layer. But the weights in one of those could have a bunch of zeros such that they're actually ignoring inputs from certain neurons, but we don't force that to happen by omitting connections. You will see in later chapters other architectures that change the rules on this in terms of either restricting the number of connections or having different connections other than just simply from layer n to layer n plus 1.
I see. Okay. Let's just stick with the basics for now then.
Okay. Yeah. I don't want to, get too far off the basic ones here. Okay.
Right.
Okay. So let me put my thing there. And this is what happens when we train. And you can watch my stupid little cartoony thing on the left here. As we cycle through more data, we start with some loss. It's usually high. And as we train, the weights and things, and that's what I'm representing by the colors changing within the neurons, get adjusted. And our goal is to reduce this. And what will happen is, as you go through, you get to the point where it'll kind of level off at a certain level, and then you'll declare the thing trained, and then you can go and test it. Okay, fairly basic. Now, this is a ultra simplification of the process, and let me show you what we call a loss space, because this looks like a nice 2D graph, right? You just Bob's your uncle. But the reality of the situation is considerably worse. This is what that space that we would be navigating down through looks like for something called resonant 56, which is just a neural network. If we're starting over like here, we can go down, and then go, oh, I've reached the bottom. But no, you really haven't. So you may sit around here and poke around for a while over in this space, and then realize, oh, I have to go over here. Well, now you're trapped, and things like that. And so the spaces can be extremely complex, is I guess what I'm trying to point out, because our end goal is to get down to here, but how you get from any given point to there is a kind of a navigation through the loss space. And there's all sorts of tricks and formulas, and Ted mentioned one, which is to kind of skip a lot of steps and get there. And the whole purpose of a lot of these is to smooth out this loss space so it's easier to get to ultimately the low error thing down here. Okay. All right, let's move on. We're going to move to a demo. Yay, I love demos. We're going to use Colab. Is everybody pretty much familiar with Colab? Colab is Google's cloud environment for developing machine learning. And they give you some pretty nice features in there. They give you things like access to GPUs and TPUs and things like that. And it's a zero cost thing. Again, just, like Google Photos, Google Gmail, blah, 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 blah. Unless you want to get more features, and they will happily sell you additional time and things like that for $4.99 a month or whatever, or more GPU access and things like that. As Ted and I believe Ryan mentioned, we're going to use TensorFlow as our machine learning framework. TensorFlow is one of the two big ones. The other one is PyTorch. And interesting, they're made from people that literally work, 8 miles apart between the Googleplex in Mountain View and Facebook's headquarters, where they make PyTorch, which is, I think it's about 4 exits up the road. So it's kind of a bizarre, and people tend to move. I've seen a number of people I know move to Google, from Facebook, and Meta, excuse me, sorry, and vice versa, Meta, whatever. So it is a very incestuous, like the rest of the valley, incestuous small world that people work in. So just so you know. And layered on top of TensorFlow, we're going to use Keras, which will be our framework that'll let us easily build the models. It'll be easier to show you. Keras originally started, the guy, Francois Chalcott, wrote it, and it sat on top of a number of frameworks. TensorFlow, I forget what Microsoft's was, we're like 3 or 4. But his, Francois and his team have been purchased, if you will, by Google. They now work for Google. And so Keras is now the easy to use interface that TensorFlow has. TensorFlow has, you can do machine learning in a more functional way, and they have functional programming interfaces that don't look like Keras and that look more like PyTorch in JAX and things like that. So anyway, we're going to use the Fashion MNIST data set. And let me show you that real quick so we can move on here. Fashion MNIST, that's what the data looks like on the left. Their clothing item recognition. There are 10 classes, and you can kind of see some. There's shoes, bags, things like that. And this is one of the classic ones. You're going to see this all the time in your machine learning. People will use this just as a base set. Fashion MNIST is produced by a company called Zalando Research. And it's a replacement for something called MNIST, which was a bunch of handwritten digits. The reason they replaced it is because for neural networks, handwritten digits were too easy. 99.7% or higher accuracy was common. So how do you compare my algorithm to yours if we're both at such high levels? Prior to neural networks, 60% was a really good score on MNIST. So you can see the quantitative jump that it's done. It's overused, and it's not really represented. The original MNIST handwritten digits were not represented in a lot of problems. Okay. Let's see, a little bit more about it, just because you're going to run into it all the time. 70,000 data points, 60,000 used for training and validation. That's to train the model and then do validation when you're tweaking your training. 10,000 are typically set aside, never used for training. You always want to have your testing data set aside for testing only. Each data point contains 28 by 28 grayscale image, so it's pretty darn low res, and we'll see some of those. And there are image classes. Being programmers, we start at 0 and 0 through 9. Some images appear different classes, and they look very similar, like a sneaker and a sandal. Okay. And we're going to kind of go through a notebook in a minute, and we're going to build this model architecture. Over on the right, we're going to start with our input data. We're going to flatten it from 28 by 20 to 784 pixels. We're going to put 300 of those neurons in the first layer, 100 in the second, and 10 in the last layer, which is what we would call the output layer. We're doing 10 because remember we had 10 classes of outputs. 10 classes of clothing items, and we're going to get the probabilities in each of those. So in this case, the highest probability of 0.85 out of 1.0 is class 8, which is a bag. And so that if we were to push this image through this model, we would hope that it would put out the class is 8, it's a bag. Questions on that? Okay. All right, let's just pop over here. I'm going to hop around some screens. Slack. Oh, here we go. Can you guys see that? Okay, this little notebook. It's essentially very close to what Aurélien, and I'm just going to launch it into Colab here. And over here, and we're going to go through this not quickly, but relatively quickly. Let's just go ahead and launch it. Yeah. I know Google didn't write this. And this is standard coding. You want to import whatever your framework is. And if you're using Keras within TensorFlow, you want to make sure you import it from there because it's also possible to use Keras separate. Okay. We're going to use Matplotlib if you haven't used that for visualization and NumPy. We just imported that, and the first thing I always like to do is print the version of those libraries, you'll know, because bugs do occur in certain versions, and we're using 2.7, which is actually ahead of where TensorFlow is. They're 2.612, I think, or something right now. And we're going to load our data. Let's go ahead and load our data here. How are we doing time-wise? Oh, we're good. We pull it in, and if you notice, Keras has a lot of these data sets, including the fashion MNIST there. So we did a load data, and it dumped the training subset, 60,000 in that, and the testing subset, 10,000 entries in these items. And if we print, hopefully, cross fingers, we get that 60,000 in the training, 10,000 in our testing. I'm going to define those 10 items into an array, 0 through 9. 0 will be the t-shirt, 9 will be an ankle boot out there. Let's see here. Let's just look at the data here. We'll just run this one. And this is the kind of what the data looks like here. You can see this is anything but high-res data. And the reason being is if it were high-res data, this is going to take long enough to train. We would be here a lot longer. So won't do that. If I'm going too fast, people slow me down, please. I just, I'm always happy to do that. First thing we're going to do is these pixel values, these are 8-bit pixel values. So they have a values from 0 to 255. We like our data to go from 0 to 1 range. So we're just gonna scale it here. Oh, and the other thing we did is we're putting the first 5,000 of those into the validation subset, and the remaining from 5,001 to whatever the end is, like 60, into the training set. So we did that for both the X values, in other words, our data, and our gray value. Yeah. Oh, somebody asked about that. If we do that, and because it should be grayscale, if we just do this, let me just show you. You can just, I think you can just do remembering it, right? That's a good question. To get the data to gray, you can just go like that. Boom. Bob's your uncle. So this just little CMap function does that. But later on, we're going to see these, and I like them better in color than in gray. So there, it's my notebook. Okay. So let's go ahead and create our model. Remember, back to our picture, we have an input coming in, And we were going to convert those 28 by 28s into 784. That's what this comment says here. And we're going to do that. We're going to create what's called a Keras sequential model. And as you can probably guess by the name, the Keras sequential model, when you add a layer, you're just concatenating. Boom, 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 boom. Okay. So here we're going to add a flattened layer, which is really not a neural network layer. It's really a processing step. And what it's going to take, as the comment says, is take our 28 by 28 images and convert them to 784. Okay, and then the next we have our dense layer. Remember we had that dense layer in the picture of 300 neurons, and we're just going to create it in one quick line, just boom, it's just going to add it to it. And you're going to create another 100 in the next layer. And notice I put these names in here. This is completely optional, but when you start building networks that are big, you get to the point like, oh, what was that? And the system will just kind of arbitrarily assign names to them. It's not arbitrary, it'll just give them a sequence. And you can then use this name feature to actually tag your things. In the last layer, we're going to, that one that was supposed to give us the class probabilities, we're going to use the softmax activation. Oh, I should have mentioned these. ReLU is the one we talked about before. Anything below 0 gets left at 0. Anything above 0 gets left as whatever it is. So it's just kind of a function to break linearity. Same here. So let's go ahead and build our model. Model's built. And then we can just take a look at the structure of it. The flattened layer, as I said, all it does is convert that data. So there's no trainable parameters. But look at here, our layer with 300 neurons in it has 235,500 parameters that we can train. So that's a lot. If you think about it, knobs and dials, like that's a lot of knobs and dials. And this is a trivial neural network, right? 2 layers. It's barely deep. The second layer, the dense layer, has another 30,100. And then that softmax at the end that gives us our 10 probabilities for our 10 classes has 1,010. It's grand total, 266,610 settings we can adjust by training. Okay, this is why there was this huge step up in performance, even on these simple data sets, because we had so many settings. We could just look at that loss space that we talked about and get in there and dig into it and tweak our models so that it did really well with it. Okay.
Hey, Jerry.
Go ahead, Ted.
Before you move on here, if we could just pause and talk a little bit about, for people for whom like Keras is new. So this sequential model, like Jerry said, you're just adding layers one at a time. And one of the consequences of that is that therefore you can only have one set of inputs and you can only have one set of outputs.
Exactly.
Now that is like 90% of the problems that we solve, but nevertheless, that's limitation. So whenever possible, I would say use the sequential way of defining a neural network because it is the simplest and the easiest. And so each time you just simply say add a layer, it's just,
it's a concatenation.
It's just concatenating. Yep, stringing them together. And so I don't remember if you added a token slide or not, but in the chapter it does talk about, well, what if you actually had the problem of 2 separate inputs or 2 separate outputs or something funky? The book does in this chapter get into it. You're not likely to need it right away, but just even if you don't play with it yet, just know it can be done.
Yeah, we'll get to the API, the other API towards the end here, and I'll just re-implement this. But Ted, you're absolutely correct. The other thing that happens in a lot of, if you're going to take this, move your models to like the high layers, I kind of alluded to this. You can skip certain layers. You can push data as multiple paths to other layers. And you can have what we call skip connections, and you can't really do that with this. But that for as Ted said, 90-ish%, especially as you're starting out, closer to 100% of what you're doing. The sequential model is fine. Yeah, we'll get to that.
So it's pretty cool. So if you've never seen neural networks before, you do a bunch of imports. Jerry has about 5 lines of code. So, total about 200 characters. And he's defined not a super complex model, but nevertheless a model that has, hundreds of thousands of parameters. Really doesn't take very much code to create a neural network.
Right, and that's why we use frameworks like Keras or PyTorch or what have you, because it does things, it makes it simple. It's the same reason we always, we could probably write a database system, but wouldn't it be better just to call a database thing and tell it to append a record and let the magic happen? Same thing. Okay, we have to compile the model, and this is not compiling if you're a computer science person, where we, convert it or anything like that. It's more like a token. It's not really tokenizing. It's more like syntax checking, making sure that you have a loss function, making sure that the loss function, remember we talked about the loss reduction function, is compatible with your optimizer. And then this interesting thing here, metrics. When we train our model, how do we know we're doing well? Well, that's where this metric comes in. Here we're saying we want to, do better on accuracy. We want to get more accurate. Makes logical sense, right? However, when we get to more complex models, there may be other things we're concerned about. And notice that this is an array. This is a Python array, right? So you could say, comma, some other metric or something like that, in here, and it would actually use both of them. I'm not going to do that because I don't have one off the top of my head, but you can do that. So you're setting parameters that will be used in training with this compile statement. I guess it's probably best we leave that. So let's set this. And this is really common within Keras, kind of this array sort of syntax. And we're going to train this now. Let me double check something here. This is going to take about a minute or two. Yeah. One of the cool things as I mentioned in Colab, is you can either, you can enable a GPU for free if you don't have an NVIDIA card. And these days, I don't know if you guys have ever looked, but NVIDIA cards are, a card that should retail for $200 is going for 2,000 and things like that because of crypto miners. So it's kind of nice they give you one anyway. And we'll get this just training here. And what it's going to do is it's going to go through our model, taking our data that we created up here, and it's pushing it through the model, and it's validating it with our validation set. Remember this said there was a validation set of these first 5,000 items. And so it's going to go through that for a minute or so. And it's pushing it through this model, adjusting all the weights in here. Flattens the data, and then for our 300 neurons, it's going through and adjusting the weights in our first tensor. And then for the second one, it's adjusting the weights in the second tensor. And then it's adjusting the weights finally in the softmax. And once again, there are a ton of weights in there. So it does take a moment or two to go through those. Let's see how we're doing here. Oh, we're halfway through. So we are running through here, and it's doing those and making all those adjustments. It's going back and forth with our training data, running epochs of the training data through there. And it's every time it gets a little bit closer. You remember that space that we looked at? Where is it here? I go back to this. This is our model, but if we go, I think I had it here. This space here, it's exploring this space, figuring out how do I get to the point that's going to get me the lowest error. So it is going to, it takes it a bit to do that. But anyway, okay, let's see how we're doing. Oh, 27. Okay, the last couple of them here. And you could say it's taken about 4 seconds to run all all of our data through there for that epic data. Okay, and we're at 30 and we're done. And this was a stupid model, and it gets 91% of on the data that it's trained on. In other words, it gets it right 9 out of 10 times the right class of those pictures. And it gets darn near 91% or 90% on the validation data that it's not trained with. Remember, this is our stand-in for our test data. So let's see how it does on real test data. It gets about 88%. So, not bad. It's getting 88%. That's a heck of a lot better than you and I guessing at those, throwing a dart at those. But let's see how this looks. My friend Margaret Maynard put this together, and I really like it for this particular one. It's a nice illustration. So what she does is she goes and just kind of picks random ones and then just visualizes them. Once again, these could really are gray, but I like them in colors just because I like them in colors. So you're stuck with that. Here's a dress, and it thought it was a t-shirt. So it put it in red. So we have two errors here. This dress that also was should have been trousers. And you can kind of see, given the resolution, I could see how it got messed up. If we run this again, it'll go figure another 10 things. And here it only got, it got two wrong here. This t-shirt should have been a shirt. Well, kind of the difference between a t-shirt and a shirt in this database is, do you have a collar? So that's pretty tricky here. And this pullover versus coat, I think the difference is like a zipper or something like that. It's very subtle. Run another one just for grins. We're doing pretty well. Oh, hey, here we got 90-ish% because we got 9 out of, I'm sorry, she has 15. So 1 out of 15 wrong. So 9, 14, 15s were correct. I don't know what that is percentage-wise. Pretty good though. Okay, so now training is correct. We can deploy this model into, some sort of application, because, we can take our trained model, take its weights and run it just as we did here with this little predict function here. Right here, trained model predict, one line of code. And then in this particular case, because we have 10 classes, you have to figure out what the class is, but it's all in this variable. So that's it. Questions on training a model, because we're done training. Anyone? Okay. I'm going to move on then to a couple of things that kind of make our lives easier. Training all of this is an iterative process, so we want to do things iteratively, and we like tools to do that. One tool that helps us is something called TensorBoard, and they have a technique called callbacks. Callbacks within TensorFlow and Keras that let us do that. And there are a bunch. We can stop earlier, and we'll see that in a minute. We can get history. We can checkpoint the model, write it out. Because sometimes when you do these in real world, I do a lot of work in GANs. GANs are those things that do deep fakes and all that. And if you do those, you might train for a day and a half. And it really, really sucks when something happens and your system breaks after a day of training. Not a day and a half, so you're not done, but a day. So you essentially have lost that day and you need to go back. So you can have a model checkpoint when it just writes out the weights every once in a while and then picks up from there. So you get, you're at 80, you can restart at 85% rather than at 0. Well, we're going to look at TensorBoard, which also works if you use PyTorch. It supports PyTorch too. So all you PyTorch fans out there, pay attention. We're just going to go ahead and train our model for just a bit. And what we did is specify some callbacks into our train. This TensorBoard callback, and we just added, once again, the braces mean an array. So we can put multiple callbacks in there at the same time. Okay, we could put 7 or 8. So we could stop early training and call TensorBoard and checkpoint and write to the history file and. Okay. So we just did this for 5 cycles because the model was partially trained. Let's go ahead and take a look at what TensorBoard gives us. Oh, and especially when you're in the Keras, well, no matter what environment you're running in. Notice I did this thing where I create this log directory and I put the time and date and all that good stuff so that we can keep track of it. This path here, logs, we're running in this environment on a Linux server. So when you start specifying directories to go hunt down, you need to use Linux types, a / here. If this were a Windows machine, what would I use? A \, right? So it is OS dependent, so I'll point that out. All right, let's take a look here and see how we did on our little thing. Hey, it looks pretty good. And we can also, but this is one thing I'll point out here. We're getting better and better. This is our validation data. You see the little, when I hover over that, if you see the little highlight on the blue dot down there, you see, or the orange dot, blue, orange, blue, orange, blue, orange. This is the validation data, and we're doing pretty darn well on that. But we really could have stopped about here because we're not going up and we want to get better on that. We'll talk about that in a minute. It also has smoothing. So it's really smoothing that graph. So it really looks a little jankier than it is. Okay, and we can do that. We can also, if we want to, this is underneath what it's doing. And if you zoom in really well, this is really, if you're into this, you can say we're doing scalar multiplication, matmul. Those people that do PyTorch, they get to code this stuff by hand sometimes, depending upon what you're doing. Or if you're using JAX in the TensorFlow world, you can code these by hand. Oh, here, division, not available. Things like that, and you can watch the data. And if you really, really zoom in, you can see how many values it's actually moving from each equation, which is kind of neat if you're into really diving into computation graphs. You can also get, this would look better if we would have, that thing where we were kind of going through that space. This is kind of a graph of that. Let's do the histograms. That's a little bit better. And you can see on each iteration, it's getting a little bit better and adjusting these values. And you can just walk through all your various layers. Now, this was such a trivial program or trivial problem that this thing really honed in on it quickly. But it's not unusual in the real world to, well, first I only did five iterations here, 5 epochs through the data. It's not unusual to have 1 million epochs or something like that. And you'll see these peaks just move around as it's trying to figure out all of the various values, and they're trying to navigate that space. Let's see. Yeah, and these are just the time series. You can create these nice little graphics to show your team and things like that based on time series. And I don't want to go too far into this, but it's really a pretty cool tool. You can even do this after the fact. You could say, write all those logs out and then have the log files, just pull them in. It's, I forget, it's not CSV format, but it's a standardized tokenized format, almost like a CSV. And that's why these logs can come from either TensorFlow or they could come from PyTorch. And you can use the same tool at it. So that's a pretty cool thing to watch, how we're doing. Could we have stopped training earlier? Maybe we could have stopped, after, well, here, literally after 1, because I had pre-trained the model. So like that. Okay. That's a little bit advanced, but no. Okay, so let's, there are 2 interfaces. We looked at the sequential interface. Let's now look at what they call the functional API, which is the one that Ted was referring to, that you kind of wire things together individually. So here I'm specifying our inputs are 28 by 28, and I'm going to do the exact same thing. So I'm going to flatten it, create our 300 dents, 100 dents, and so on. But what I want you to notice is I'm creating these as a function, and I'm getting a pointer to these things in the name of a variable. So now I've got my 28 by 28 input shape input layer, and it's in the variable inputs. Now I pass to my next layer that variable. So I'm passing that input to it. So if I had, let's just call this, we'll just call it x2, that'll come on. So I could create Keras dot layers dot dense, maybe 5,000. That's a pretty reasonable one. Activation. Gosh, I can't type today.
Misspelled Keras.
Oh, there we go. There's the problem. Thank you. How many people does it teach me to code? Obviously, more than one. Lulu? It's a constant, so we're not going to get any help there. I could also pass this to inputs to that. Okay, now I've got two, if you will, parallel things that are going to process that input. Okay, does that make sense? It's just that easy to do that. But as Ted pointed out, if you're starting out, you're probably not going to need this. You may need it as you go on to more complex models. Yeah, I'm just going to, well, I'll just comment it out here just for the sake of argument, just so we have it. Okay, but what we're going to do is we're going to now take our flatten layer and put that into X, pass that in to the input of this. The other thing you can do is, let's say for some reason you wanted to have a conditional. Nothing says you couldn't put a Python if statement here and then say, oh, no. If it was MNIST data, I only need, because it's so trivial, 30 in the next layer, 30 neurons in that. So I could say if it's MNIST, not fashion MNIST, then go down here and do, same thing. Let's just do this here. Something called model equals M. Did I copy? Let me help there. My Python sucks. But you could do like that, and you could just, make some decisions here about that. Okay. All right, we're going to take that out of there because that's going to break us. Okay, but anyway, here's our model as we have it. And this one is mirroring our other one. And every time we output it to X, this is really common to reuse this variable, and you just wire it together. Here's our 300 coming in, gets wired to the 100. Here's our 100, gets wired into the south max. Okay. And then we're going to just hook it up and print it out and compile it. So now if we do that, here we go. We have our input layer, our flatten layer, blah, blah, and we have our 266,610 parameters, just like we did before. And we can go ahead and train that. Oh, but wait, this time, you remember we went like 30 or so last time, right? But realistically, we didn't need to go that far. So what I'm going to introduce here is an early stopping callback based on validation accuracy. If it doesn't change, that's what this patience is about, in 3 cycles. In other words, if it goes, we're going higher validation accuracy, higher, and then it goes lower and lower. And, it doesn't bounce back up to a higher one than we've seen before. It's going to stop and say, oh, we've gotten as good as it's going to get. And then what it'll do, because I set this restore best weights to true, is it'll back up to those two, to the last ones. And that's where it will cut off the model at our highest value. So if you think about this, if you're running these models and they go, if you run models, they'll tend to vary, you know, like their accuracy or whatever metric you're doing over time, and it'll get better and worse. Nobody write this code down. I'm going to give you the pointer to my notebook and everything like that. So don't anybody write this down. We're going to also do the log thing again. And here we see we have our function. And here, remember, it's an array. So I have both callbacks on that array. I'm going to do the early stopping as soon as we get. And I'm also going to update the data, call up TensorBoard, and pass that data to it. Okay. So let's let that rip. And it'll run for a few moments. And what we should see, you know, given the demo gods are with us, you should see, you know, I set this to run for 30 epochs right here. You can see this number over here. Actually, it was specified. Anyway, oh, here it is, 30 epochs. But it should stop sooner than that. Don't make me a liar. Don't make me a liar.
So one thing I want to touch on here, if you scroll back up to the model definition section, Keras actually does this sort of magic thing that simplifies things a lot, where it will infer what the shapes should be. So if you do stuff in raw TensorFlow or PyTorch, sometimes what you might have to do is you have to define an input shape and an output shape, because it has to actually do a matrix that says, okay, you have 300 inputs, you're going to do a matrix that goes to 100 outputs. And Keras does both sides of that for you. So it just knows I'm going from 300 neurons to 100 neurons. So I'm going to make a matrix that converts between 300 and 100. And you don't have to worry about a bunch of shape mismatches and stuff like that. So Keras makes that a lot easier.
Yeah, I mean,
the input size, the output size, the number of parameters, and it hooks everything up for you.
Yeah. Yeah, if you ask Francois about that, you know, he'll say, you know, that was one of his design things with it. And simply because it bothered him so much that, you know, it'd be like this trivial sort of, oh, you were off a little bit in the parameter thing. So he spent quite a bit of time, and his team does now, trying to make this as easy to use so that you can focus on structure, tuning, you know, rather than the plumbing kind of the system here.
I forgot who it was, but one of the top AI guys made a tweet a while ago that was basically like, if you're just guessing and checking on shapes on these things, like that's what everyone does. So it like there's a lot of complicated things where it's like someone's doing a convolutional layer and then you don't know what it's going to be on the output depending on what the input shape is, and then you have to do all of this crazy math trying to figure out what the output shape is going to be. And even the top people, you just basically just pass the input through and then it gives you an error and you go, oh, I did the size wrong, and then you try something else, you try to get it to line up correctly, and Keras kind of solves all of that for you because it understands the underlying math behind it.
Yeah, which is good and bad, right? Depending upon what you're doing, because maybe you really did expect the shape to be output shape to be a certain shape, and then it will, you know, hook the plumbing together, but you know, maybe it's the wrong plumbing or something like that.
Yeah, that's possible.
Yeah, earlier versions of Keras didn't have special layers where you could define ways you want to peel apart, combine, change, you know, your data. So then you were limited to the auto plumbing functions. I think as Keras has grown now, you know, like you saw, flatten can take something that's square or rectangular and turn it into just a one-dimensional thing. And you can, I think you can go the other direction as well, and you can concatenate things, and I think you can split things. So it's gotten easier and easier now because, again, like Ryan's saying, it does all the math for you. But whenever you do need that occasional thing where you want to do something a little funky, it does. I think the later versions have special functions you can use for that.
Right.
Are you talking about like if you wanted to call X2, if you scroll up to that code, if you wanted to include that X2, it would automatically do it in the auto plumbing?
Yeah,
Yes.
if you say X2 is an input to something else, it'll just figure out all the plumbing to connect them.
Okay.
Yeah.
Right. But so like for example, I had something where I was playing around with a color image and I said, oh, what if I just pass the red channel to the next layer and don't pass the green and the blue, right? So I basically needed to chop off 2/3 of my data. Early Keras, you couldn't do that. I think maybe now I've never actually done it, but I think there might be a special tool where you can say, hey, do this kind of crazy thing to my data, just chop off 2/3 of it.
Yeah, a lot of that has to do because in the early days it was Francois and Francois only as a passion project.
Yeah.
A single person can only do it. Now he's a team leader, and I don't know how many devs he has under him. But he has help these days because it's heavily used, within Google. It's a lot of, like TensorFlow and Keras started as internal Google tools. They're very, very heavily used in the company to run their business. So, I'm sure he gets hate mail from internal developers. Why does your thing do this? But anyway, let's get back through this so we can finish this up. So we did our thing. Remember, we specified early stopping in the tensor board. So and we can see here it said, it says we went out to epoch 19 here, and it says, it didn't get any better, and you said it had to get better in 3, right here in this patience parameter. So it didn't get better, and it said, nah. So I'm just going to restore the models back to epoch 16. Okay. So it looked at that and said, we're just going to do that. So this, I cannot stress enough how cool this is. If you have a model that's a long running model that's going to run for a long time, it'll go off and it'll look like it's getting better and things like that. And, I just can't stress how much, after 20 or 30 hours of running, that you could have stopped at hour 5 and then gone on is such a big win. Let's evaluate it and see how well this does. And it gets 87%. And let's use Margaret's little function again, our little routine that I put in a function, and see how it does on some random data. And it got 9 out of 15, or 14 out of 15 right. So it's doing quite well at its guesses here. Run another set through. I shouldn't say guesses, prediction. Sorry, excuse me. Bad thing. And then let's run TensorBoard again. And TensorBoard is now starting up some processes in the background, so that can take a bit here. Here we go. Okay, and in fact, let's look at the accuracy. And once again, I'm looking at validation accuracy here. Let's just take the smoothing off, and you can see how janky that is, right? It's going up and down, it's getting better. And here it gets worse, right? It goes down. But because I set that patience parameter, I said, no, you've got to have 3 of those things going down. It kept going and it said, oh, hey, it's getting better. So it continued on. So it made that logical jump. I didn't have to do that other than being smart enough to set the patience to a reasonable amount. That's a huge win, because normally if you code it like, as soon as you get max and it starts going down, you'd be, you'd have a problem. I don't remember if I did loss or accuracy, but whatever metric I did, I could have used either one or both of them. Okay. So I wrote some other things here on the notes here. Separate parallel model structures. We talked about that. Multiple branches repeating segments. This is common when you get to more advanced stuff. And the models are getting more and more complex. And a lot of times these days, if you've used a lot of the tools, they have like an auto ML capability where they're generating actually your model for you based on your data inputs. And the functional API is real good for wiring those down. All right, so that's the end of that. And let me just, I have a couple of slides to go through. Questions on the hands-on. Everybody good? Okay.
That was great. Thanks, Jerry.
All right. Yeah. So we did the demo environment, blah, 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 fashionness. Sorry. We've seen all this. We did that. Oh yeah, I'll put that up there. There's this whole section, little section in this chapter, but you're going to spend more than about tuning your networks to perform better. And here's my quick 1 minute thing on it. It's based on experience, and it really is, to me, as much art as anything else. Because we have so many things we can adjust. We can adjust the data, we can adjust our arrangement of layers, types of layers, number of hidden layers, neurons per layer, hyperparameters, and those were things like our batch size or learning rate, all sorts of things like that. And what happens is, if you work in a specific set of data, you sort of develop a feeling for, oh, we're not doing well on, you're working with image data on these particular types of image, so maybe we should try to tweak this parameter and things like that. And they do cover this in later chapters. And that is the end of my presentation. So with that, I'll stop sharing, Ted, and give it back to you and Ryan.
That's awesome. Really, really great job, Jerry. Yeah,
Thank
I'll
you.
also add just a comment that since this book was published about 2 years ago, there's much more now in the way of pre-trained models that you can use as a starting point instead of training something from scratch. And so I think there's less of a need these days for people to learn, like picking like how many layers do I want and what architecture. That's less common versus just using something kind of off the shelf and then maybe having to train it, but not having to design the architecture of that. So when you read that chapter, some of those choices aren't really things that you need to learn. If you're going to be a researcher, right? If you want to like go work for, UC San Diego and research something, then yes, you will need to learn all that. But to just be a practitioner, you don't necessarily need to do too much of that.
Yeah, I think that's a good point, Ted. And if you work for a company, let's say you work for GM or some big company, and you have a certain goal, your boss has said you want to come down, and you need to create the best model for that. The cloud providers are creating tools for that they will sell your company, at so much a minute, so much an hour, or whatever. This whole AutoML suite, where you put your data in, and it kind of runs all these models from, some of the basic ones that we talked about in the previous section, up through very, very large neural networks, and figure out what is the best way to go for that. So,
yep, awesome. Hey, thanks again, Jerry. This was a tough chapter, a lot of material, and I really liked your slides. I really liked your presentation, and thanks for actually walking us through some real code so we could see like the models actually training and stuff. And I put a message in chat. I'll get up on the repo. I'll get your slides and the link to your Colab notebook up there.
Okay, great. Yeah. Yeah.
I'm just want to
yeah. I'm sorry.
I just want to mention something about the data, because I worked with it like I think 4 years ago. And it is very bad data. Only at the beginning, it looked like the data is well classified, but I got stuck on some particular way, how much it was, 95.5% of accuracy, and I could not move any higher from this. So I ran it many times, and I did a lot of pictures of wrongly classified data. What I discovered there is there are a lot of women tops, which cannot be exactly called as a short or T-short. So they, from my point of view, well, if you do confusion matrix, you will see that these things are often misclassified with each other. And at some point, I saw in the data a swimsuit, well, one piece, but still it was a swimsuit, And I even have seen a mannequin there, which was, well, because it was shrunk so much and the picture was grainy, I couldn't understand what the mannequin was wearing. So the data is not very good, but thank you very much for your presentation. It was fantastic. Okay.
Yeah, the 28 by 28, let me just say about using image data, because I do that. There is a natural issue. You know, a 4K image would be great, right? And you could probably train a great model, but it would take you forever because you'd have, you know, what is that, like 2000 by whatever it is, pixels to run through the thing. So you usually, you know, you're down to like 300 by 300 or something like that. And even then it takes a while. But you're right. Yeah, as you lose resolution of the image, the model can only garbage in, garbage out is probably the best way to phrase that. If you give it a really janky looking 28 by 28 picture, do not expect 100% perfection on what that is, you know, in the image recognizer. So it is what it is.
Yeah, awesome.
Okay.
Okay, so what we're going to do now is we have these officially two different meetups set up back to back. And so thanks for those of you who joined us. The book club does sometimes run over. So welcome. So we're going to transition now to the project collaboration meetup. And it's perfectly fine to ask questions about Keras and the stuff that we were just talking about. But we're also going to welcome other people who've joined. And we can talk about anything, coding questions, projects at work. So Ryan may share a little bit about something he's been working on. If we have time, I can share a tiny bit. I haven't had time to work on it, but I was looking at a publicly shared notebook on Kaggle for one of the competitions that I've been looking at. And I can say, I didn't do much, but I could say share maybe like, 2 minutes, 5 minutes of comments about that notebook. But so what we do at this point usually is we just open the floor to see if people have some question they want to ask or something they want to share from some work that they've been doing recently. So if you were with us for the book club, you're not staying, feel free to drop here, and I'm going to open the floor. Oh, Ryan, we can stop the recording. And then